Okay, so for 5.2, we're going to actually be talking about exponential functions and identifying exponential functions. We're going to look at equations of exponential functions and all that good stuff. We talked about in our function families packet. Now, you should still have your function families packet from like the first week of school. I told you that you were going to keep it forever, right? Okay. The exponential function family is of the form y equals a times b to the power of x. I will tell you what those letters stand for in just a second, but first let's look at these three tables below. Look at your x values. To get from 0 to 1, what would I add? 1. And then to get from 1 to 2, what would I add? 1. And then from 2 to 3, 1. 3 to 4, plus 1, and 4 to 5. Okay, what about to get from 3 to 9, what would I add? To get from 3 to 9? 6. What about 9 to 27? What would I add there? Plus 18. What about 27 to 81? Plus what? I didn't ask what I multiply by. I said, what do I add by? 54. And what about to get from 81 to 243? 162. And then 243 to 729. 486. Okay, so my question to you is, do the y values have a constant rate of change? No, because we're not adding by the same number every time. What are we actually doing? Multiplying by 3. Okay? That means that this is not a linear function. A linear function was when we had a constant rate of change, meaning that we add the same number every single time. Multiplying by something does not give you a constant rate of change. Look at the second table. Do my x values have a constant rate of change? Yes. Do my y values? No. No. What are you multiplying by in the second table? 2. Times 2 every single time, right? Okay. And then look at table number 3. Do my x's have a constant rate of change? Am I adding the same thing every time? Yes, so they're all plus 1, right? That's important. Do my y values have a constant rate of change? No. What am I multiplying by every time there? Times 5. So that's the difference between a linear and an exponential function. In a linear function, your x's and your y's both have a constant rate of change. That is called the common difference, because you're adding every single time, right? For exponential functions, our x's should have a constant rate of change. They're adding 1 every single time, but my y's do not. My y's are being multiplied every time. That's called a common ratio. Ratio is another word for multiplying and dividing. Common difference is another word for adding and subtracting. So when I give you the generic form of an exponential function, A is your initial amount. Or, yeah, initial amount. Another word for initial amount is like your starting value. Initial means the first one. So in this first table, what would be the initial amount? 3. In the second table, what would be the initial amount? 3. In the third table, what would be the initial amount? 2. Initial amount is where x equals 0. Okay, so I want the y value where x equals 0. Sometimes your table might start with a number different than 0, but we still use x equals 0 for your initial amount. Okay? B represents the number you are multiplying by. Okay, so B is the number you are multiplying by. So in table 1, what number were we multiplying by every time? 3. What about table 2? 2. So the B would be 2. And what about table 3? 5. So the B would be 5. X is going to be the number of times you multiply. Okay, so when I ask you to plug in a certain number for x, that means the number of times you multiply by that number. Before we get started, label these tables A, B, and C for me. They're the exact same tables as on the previous page. Yes, so what they want us to do with these is to go 2x values further in both directions. So instead of starting at 0, I also want to find -1 and -2. And at 5, I want to go to -6 and +7, or not -6, 6 and 7. These two should be easy. In the first table, we were multiplying by 3. So how would I go from 5 to 6? Times 3, and that's how they got 2,187. And what about from 6 to 7? Times 3. Okay, that's how they got 6,561. Now, our original table started at 0, so how do I go backwards multiplying by 3? Divide by 3. Dividing by 3 is the same as multiplying by what?
1/3.
1/3. So that's the same as saying times 1/3. 3 divided by 3 gives me 1. 3 times 1/3 also gives me 1. What about if I go backwards one more time? What's 1 times 1/3? 1/3. 1 divided by 3 is also 1/3. Okay? The reason why I want to point that out to you guys is once we start writing the equation for these exponential functions, the common ratio, or the number that you're multiplying by every single time, sometimes the numbers will be getting smaller. So sometimes, instead of multiplying by 2 for every single one, I will be dividing by 2. However, when I plug that into the equation, if I put just 2, that implies that you are multiplying by 2. Does that make sense? Not dividing.
Yeah.
So in order to show that we're actually dividing by 2, you multiply by 1/2. Okay, so just start getting used to talking in only terms of multiplication, not necessarily division. Let's do table B together, and then I'm going to have you guys do table C. Table B, we were multiplying by what? 2. So to get from 5 to 6, times 96 times 2 gives me what? 192. And then to go from 6 to 7, 192 times 2 gives me what? 384. Everybody good with that? Okay, let's do -1 and -2. To go from from 0 to -1, I divide by 2 or multiply by 1/2, and what would that give you? So 3 times 1/2. 3/2 or 1.5. And then to do that one more time, what would I get? 0.75. Okay, do table C for me. Okay, so there are the values for table C. We should all be good with this? Okay, the next thing we're going to do with these is we're going to graph them. So for number 2, I did 3 graphs, one for each one. My x-axis just goes from -3 to +3, and my y's, I went from 0 to 10. So draw your graphs for me right now. Okay, so to graph these, we already have a table of values. It's okay that our graph will not cover everything that's on the table of values. I do not expect you to graph y all the way to 6,561, okay? So whatever fits on the little sketch graph that we have right here is good enough. Now, can we do -2 and 1/3 on there? Yeah, we can. -2 is left 2 spaces, and 1/3 means 1/3 of the way up. So not quite to the 1 mark. The next value on the table was -1, 1. So -1 up 1. What's the next value? 0, 3. So up 1, 2, 3. And then the next one is 1, 9. And mine, I know mine goes to 10, so it's going to be right here. Okay, does that look linear to you? No. Definitely not. So we connect these using a smooth curve. And then my question to you is, will this graph ever cross the x-axis? No. Why? Let's think about it. What are we doing to get smaller every single time? Dividing by 3. As long as I keep dividing by positive 3, will this number ever become negative? No, because a negative or a positive divided by a positive is always a. Now, will it get super, super small? Yes, but it will never actually cross the x-axis. You'll never get negative values for y because all we're doing is cutting it into thirds every single time. So I will eventually get to like 0.000000001 or 100 zeros and then a 1 or whatever, but it never actually goes negative because we're not dividing by a negative. So that's what we call infinitely close. Okay? We're going to graph B together, and then I'm going to have you guys graph C by yourself. So for B, we're at negative 2.75. So 0.75 is the same as 3/4. So it's 3/4 of the way up to positive 1. Not quite there, but almost there. What's the next point? Negative 1, 1.5. So that's 1.5. And then 0, what? 3. And 1, 6. 1, 2, 3, 4, 5, 6. And then 2 goes off the graph. So we're just going to be good there. And then connect it with a smooth curve. Guys, what function family does this look like? Exponential. Are these graphs so far increasing or decreasing? These are increasing ones. I want you to graph C for me now. Now realize 0.08 is very close to the x-axis. Okay, so it's okay. All right, so your graph should have looked like this. So negative 2.08 is very close to the axis, but it doesn't touch it. Negative 1.4 is about halfway. And then we have 0, 2, and then 1, 10. So that one climbs pretty quickly. So then the next question was, explain why there are negative values for x but not for y. Can we plug whatever we want in for x? Yeah, that's why we can plug in negatives. But why can't we have negatives for y values? Exactly. So y is the result of the equation, or when we're dividing by a positive, it's not going to change the sign to a negative, right? So just off to the side, let's write that. There are no negative values for y because you are dividing or multiplying by a positive number each time. Okay, so as long as we're multiplying a positive by a positive, you're going to get a positive no matter what, even if it is getting smaller. Okay, so then part 3, it wants us to, for each of the tables, identify the starting value A and the common ratio B, and then it wants us to write the equation, and you check a few points to make sure that that equation is correct. Now, there is a typo on this. The starting value for A is not 1, it's 3, because at x equals 0, we get 3. I don't know why it said 1. Okay? So using that function, the parent function for the function family, f of x equals a times bx, for A, A is the starting value. For graph A, what is the starting value? 3 times B is the common ratio. What's the ratio in table A? What are we multiplying by each time? 3 to the power of x. So we think that that's going to be the function equation. How can we be so sure? We can make a table to check. So make an XY table for me. But I'm only going to make you plug in 3 values. -1, 0, +1. So if we plug in -1 for x, that's y equals 3 times 3 to the -1. Guys, what's 3 to the -1? 1/3. So that's 3 times 1/3. 3 times 1/3 gives you 1. So the point is -1, 1. Is that point on the table? Yes, so put a check mark next to it. Let's check 0. So 3 times 3 to the 0. 3 to the 0 is 1, and 3 times 1 gives you what? 3. Is that point on the table? 0, 3? Yes. And then 3 times 3 to the first. 3 to the first is 3. So 3 times 3 gives me 9. Is the point 1, 9 on table A? Yes. So that is the correct equation. So we're just checking. Okay. Okay, so look at table B. F of x equals, what's the initial value for table B? Also 3. Remember, the initial value is where x equals 0. Times, what's the common ratio? 2 to the power of x. So we think that's our equation. Let's double check it. So you're going to do -1, 0, 1. So I want you guys to check those 3 points for me. And then do part C. Come up with the equation and check. Okay. Our equation for part B checked out when you plugged everything in. What did you guys get for the equation for part C? F of x equals?
2 times 5x.
2 times 5 to the x. And did that one check out? Yes, good job. Okay, that's 5.2. I have a couple questions from your homework that I just want to go over with you really quick, just because there are some questions that aren't asked in that exact way. So will you please look at your homework packet number 7. So your homework packet number 7. So question number 7 on your homework packet asks you to evaluate for the given value, and then it gives you the function f of x equals 5 to the x for x equals 4. Evaluate is another way of saying plug it in and simplify. Okay, so basically all you're going to do is you're going to write this in function notation. So if I'm plugging in x equals 4, when I write it in function notation, I have to write f of 4, right? This is telling me what I'm plugging in for x equals 5 to the power of 4. You can do that on your calculator. So if you are using one of my calculators, to do 5 to the 4, you type in 5, that's your base. And then there's a button right here that says x to the power of y. You press it, and then you put in your exponent, which is 4, equals 625. So f of 4 equals 625, and that's your answer. Okay? So you are supposed to do number 8 on your homework. If you have a calculator that looks like this, to do the exponents, you type in your base, and then to raise it to any power you want, there's this little arrow thingy right here. It's called a caret. You type it in, and then put your exponent. So this means 5 raised to the power of 4, and then you press equal, and it gives you 625. Okay, so whichever one you're using, that's how you do exponents. Okay. Let's also look at number 16 for me. So I'm going to put it under the dot cam for this one. Okay, I'm not going to do it, but I want you guys to underline a couple things. Number 16, it says, a new car cost $15,000 to build in 2010. The company's financial analysts expect costs to rise by 6% per year for the 10 years they are planning to build the car. So they take, basically, you're taking 6% of the previous year and adding it. So it's an exponential function because we are multiplying by 6% every year. The cost to build the car can be modeled by this function. So they give you the function. F of t equals 15,000 times 1.06 to the power of t. And then here's where I want you to underline. T is the number of years after 2010. How much will it cost the company to build the car in 2017? If T is the number of years after 2010, what am I going to plug in for T? 7. Because 2017 is 7 years after 2010. I just want to point that out so that you guys don't try plugging in 2017 for T and then getting frustrated because your calculator doesn't go that high, okay? Because that's way too big of a number. So it's the number of years after 2010, okay? Okay, I'm also going to do with you number 17. Okay, number 17 wants you to evaluate the function that's given over the domain -2, -1, 0, 1, 2, 3. That means that we're going to plug all of these numbers in for x and find the range. So we're looking for f of -2. You might have to use scratch paper. Some of these are simple and you can do them in your head. -2 would be 3 to the -2, which is the same as 1 over 3 squared. And what's 1 over 3 squared? 1 over 9. Probably the rest we could do in our head, but I'm going to write them down. F of -1 is 3 to the -1, and that's what? 1/3. What about when I plug in 0? Anything to the 0 is 1. F of 1 would be 3, and f of 2 would be 9. What do you guys notice? Oh, wait, and we need f of 3. F of 3 is what? 27. What do you guys notice? It's times 3 every time because it's exponential. Okay, what did I get for f of 2? What did I get for f of -2?
1 over 9.
What did I get for f of 1? What did I get for f of -1? Okay, so what did we get for f of 3?
27.
What do you think we would get for f of -3?
1.
Okay, so how do I write this as a range? Curly bracket. 1 over 9, 1 over 3, 1, 3, 9, 27. That's how you're going to write your answer. So when it asks you to evaluate over the domain, I want you to write the range in those curly brackets as a set, okay? And in order that we plugged them in. It also will ask you, even though I didn't write it down, if the function is increasing as the values of the domain increase. So as we go from left to right, do the values of the range increase or decrease? Are these range values increasing or decreasing? Increasing. If they happen to be flip-flops the other way, then it would be decreasing. So if they're getting smaller, okay? We're going to do 27 and 26, but I'm going to go in the opposite order. They want you to solve this. Now, the main goal for you right now is to get whatever term that has the exponent by itself. And then we're just going to use guess and check to solve for x at this point, okay? So if I have 4 to the x plus 4 equals 68, what do I need to do to get that 4 to the x by itself? Yeah, so subtract 4, and that gives me 4 to the power of x equals 64. Okay, so right now, we're just going to use guess and check. 4 to the x, what would I plug in for x to get 64? Or 4 to the what gives me 64? 4 to the 16? Let's try it. 4 to the, I'm hearing a lot of 4 to the 4th. 4 to the 4th gives me 256. Let's try the 3rd, 64. So then we get x equals 3. That's all you have to do for right now, is just use guess and check, okay? So let's try 26. This is 5 times 2 to the x. So how would I get 2 to the x by itself? Divide by 5. So 2 to the x equals, what is 40 divided by 5? 8. Okay, 2 to the power of what gives me 8? 3. So x equals 3. That's all we're doing at this point. Okay? Okay, that's 5.